with that, I'm going to start today's talk. This is joint work that I've done with Alistair Rutledge at Leeds. So I was at Leeds before I came to Oxford. Edgar Knobloch from Berkeley, Andy Archer from Loughborough University, and Pakwan Riapan, who was a PhD student with Alistair before I arrived at Leeds. So the talk is going to focus more on complex spatial patterns. And by complex, we mean beyond the normal patterns in that we normally look at or think of, which involve probably stripes or hexagons and things like that. So with that, I'll start. Okay, so generally, there is a wide variety of patterns that are possible, and usually systems that are not at equilibrium display patterns, and we can see them in a variety of lab experiments. Here we see a collection of few of such experiments, and the interesting thing about these is when we want to describe these patterns, what are the things we're going to look for? And the first panel that you see on the top line involves granular media. So it's basically sand, which is being vibrated up and down. And here you're seeing spatially localized. So the pattern of this little Gaussian little peaks are found not all over the domain, but only at certain locations, and they change with time. So they could be time varying, they could be spatially localized. Or in the second panel, we see results from convection experiments, and we see rolls. And here it is much more simple. Nothing changes in time. And what we're seeing is differences in temperature fluctuations. And we see that they are very ordered in terms of just stripes. You have a dark line and a white line and so on. And in the third panel here, we have a picture from a Taylor-Couette flow with wavy vortices. And here it is still rotating. So it is still moving in time, but the pattern itself doesn't change with time. So it is another kind of a description. The bottom two are a bit more interesting patterns in the sense that they look more dramatic. First, we'll talk about the two spiral patterns on the right. And there, clearly, we can see that there is two different wavelengths that are present in this system when it's making patterns. So we could say the system likes to make patterns in different wavelengths, and at least spatially at different locations, it has made patterns with different wavelengths. And in the left panel here, it's an example of a Faraday wave system, which involves taking a thin layer of fluid and vibrating it up and down with large forces. And what happens to the surface is that the surface stops remaining flat and starts to form crests and troughs, and which are being visualized here. All the white reflection comes from the flat part of the crest at the top and the flat part of the trough at the bottom. So you're seeing both the crests and the troughs in this picture. And there is a story behind the zigzag shape of this picture that you're seeing, because originally the experiments were done in a circular domain. And when they tried to publish, apparently the editors asked them, oh, how much of such a complex pattern is the effect of the boundary? And so Frenchmen being Frenchmen decided to take the map of France and perform the experiment again and show that this kind of a complex pattern is robust to being independent of the domain shape. And that's a nice kind of a response to a reviewer, I think. So yeah, and here in this pattern, the thing to note is if you look at the center of the domain, roughly the center of the domain, you see like a big circle, and surrounding that circle, you see 12 pentagons. So it's clear that in this case, the symmetry is not very simple, like a stripe or hexagons. It's much more complicated. In this case, what we have here is a quasi pattern, and it's a dodecagonal quasi pattern because it has 12-fold symmetry. So we can have quite a few different parameters by which we can describe these patterns that are formed, even in a lab experiment. And we're more interested in the patterns like the Faraday wave pattern we've just talked about. We're interested in patterns that are complex in terms of their symmetries, and we'll see how that relates to how we need to model them. So that's what we're going to do. But before that, if we want to model a simple pattern forming system, the prototypical example that we all learn is that of the Swift-Hohenberg equation. And this was originally inspired to model thermal fluctuations close to onsets in convection. And it's just a simple PDE with one scalar field, U, which varies as a function of space and time. And we see here that the linear operator, which is the first two terms in the right-hand side, have a linear growth rate mu. And the second part of the linear operator is the part that actually selects a wavelength. This way of writing a selection operator then chooses, in this case, a wavelength k equals 1. If we were to change the value of the number here from 1 to being some q squared, we would be selecting wavelengths of length q. And the nonlinearities chosen in this model really change the behavior that we expect or can produce. And in the first instance here, we've chosen simple polynomial nonlinearities, and therefore we have a quadratic and a cubic term. The quadratic term has a strength indicated by capital Q, which then is used to break the symmetry of u going to minus u. Because if we had the case capital Q equals 0, this entire right-hand side, you can flip, you can flip u to minus u and it would still remain the same system. So when we have a PDE and we want to analyze the PDE as a pattern forming system, there are the first line of attack would be doing a linear stability analysis. Throw away the nonlinear terms and try to understand what the linear behavior of the system is, and then slowly bring back the nonlinearity by introducing a weakly nonlinear analysis. By that, what we mean is we rescale this variable u and space and time to kind of talk about long-term behavior, excuse me. And then we could also take the PDE, discretize it, put it in a periodic domain for simplicity, and just give it a random initial condition and march it in time. So numerically simulate the behavior and see what happens. So these are the kind of tools that we normally use to study pattern forming systems if we are trying to understand them in terms of model PDEs. So let's talk more about this complex patterns. And here we have a picture, which is the results from Faraday wave systems again. And we see on the top two panels distinctly different patterns. And this is how the real space or the actual pattern looks like when you look at it. But you can also look at the Fourier spectra of these patterns, and they also kind of look distinctively different. They have some commonalities. The Fourier spectra both seem to have two well-identified rings in Fourier space. So this indicates that we have a second length scale in the problem. And we also can count the number of peaks on each of these circles. And in panel C, we see that we have 12 clearly defined peaks on the outer circle. The number on the inner circle is not so clear in this picture, but trust me, it's 12. We'll look at it later. And this pattern where the ratio of the two circles is, let's say if we take the outer circle to be 1 and the inner circle value here is 0.5176. So it's basically greater than a half. And by that, what does it mean qualitatively for pattern formation is that we can have two of the larger wave vectors adding up to a shorter wavelength, as shown in the picture. But in turn, we could also have two of the shorter wavelengths. For example, I don't know if I can write on top of this, but we could have two of the small gray circles that we can find close to each other, and they both will add up to the darker peak in the outer circle just outside them. So that means we can have two-way interaction via nonlinear terms in the model. And that's the kind of importance. We'll talk more about modal interactions in the next few slides. Whereas if we look at the panel D in this picture, we see that the ratio of these two length scales, the outer circle being 1, the inner circle is clearly less than a half. And because of that, what we can have is only one-way interaction in the fact, as shown here, that two of the large wavelengths can add up to a small one, but two of the small will not quite add up to one of the large wavelength vectors. So these are qualitatively different, and we will talk a bit more about both of these cases, but the specific names for these patterns exist. And in the first case, panel A is what is known as a 12-fold quasi-pattern, and the panel B is what is known as a superlattice pattern. And by superlattice, we kind of can look at it this way. We can see clear hexagons or honeycomb patterns in this picture. And there seem to be super clusters of said hexagons, which are themselves arranged in a hexagonal grid. And that is why we kind of call them superhexagons or superlattice patterns. Superlattice is a more generic term. So yeah, how do we model this in a PDE model? We can go back to our Swift homework, be inspired by it, and say, okay, in this model, I want to have 2 length scales and not just 1. And that is what Lifshitz and Petrick did. As we see here, the nonlinearities are the same as the ones that we saw in Swift Holmberg equation. The first linear growth term is also the same. It's just that the selection of wavelength now has an additional term, q squared plus Laplacian the whole squared. So this kind of a modeling approach is what kind of started to explore what happens when we have 2 length scales. But of course, we can look at this and say, oh, but wait, both of these wavelengths will have positive or negative growth rates, but they will always be equal because there is only one term mu times u. So in some sense, this model does not have independent growth rates for the 2 wavelengths. So we cannot explore this codimension 2 point in more detail, and therefore we might do better if we were to devise a model, a PDE model that has a linear operator L that can accommodate 2 independent growth rates. And so we try and derive that. We're going to talk about it in a few slides down. But then once we've done that, it's the same tools that we talked about: linear stability analysis, weakly nonlinear analysis, and simulations. We can also do more fancy things like do numerical continuation, but that's the kind of tools that we have in our toolbox to look at pattern formation in such systems. Okay, so with that, we try and look more into how we might think about nonlinear terms influencing pattern formation. In order to do that, let's do a modal decomposition of our scalar field U. And we have here the expression written in terms of capital N wave vectors at length kj and capital M wave vectors at length ql, of course, with their complex conjugates. And each of these modes, or each of these wave vectors, kj and ql, evolve in time with their independent amplitudes, which are given by zj and wl. So z's are, in this case, the lengths, the amplitudes of the wave vectors at the outer circle that you see on the right panel, and wj's are, in general, the amplitudes of wave vectors at the inner circle in the right panel. So that's, in this way, what we're doing is really taking an infinite dimensional PDE, projecting it onto these few finite number of modes, and we can derive associated ordinary differential equations, a finite number of them. And to do this properly, we use the method of weakly nonlinear analysis, where we rescale our scalar variable, time and space, and then expand the scalar field as shown here, and we will end up with ordinary differential equations, which we can then analyze. So that's the whole procedure. But before we do that, what are these, what is this analysis kind of dependent on? What are the choices that could really change what we are analyzing, or what we need to keep in mind? And the first thing is definitely the choice of lattice. If we were to choose a hexagonal or a square lattice, we are really looking at, in our finite grid in Fourier space, we would be able to access different symmetries. So in this case, in the panel on the left, we have a hexagonal grid shown in blue circles, and superimposed on them are the first three groups of wave vectors that have the same wavelength. So if you consider the central point that is unmarked to be the origin in Fourier space, the 6 orange crosses are the wavelengths that have k equals 1, and then we have the yellow ones that are 6 outside them, and then we have purple that fills out the second layer of the hexagon, and then we suddenly have not 6 but 12 wave vectors at the same wavelength. They're marked in green. So this is kind of interesting because if we can consider the first 6, which are in orange, and the 12 that are marked with green crosses, they are oriented in the same way as the wave vectors we would like to understand, as shown in the right panel, because here we see that we have 6 wave vectors of length q, and we have 12 wave vectors of length k. And at this choice, if we calculate the ratio of the radii of the 2 circles that we've drawn, we see that this is a nice number, a nice rational number, which is 1/√7. And this is interesting because this is corresponding to one of the grid states that were observed in experiments. So basically this corresponds to the Fourier spectra in panel D, which also has 6, not the 6 that you see, but the 6 under the dashed circle, and 12 wave vectors in the outer circle, which are not equally spaced, right? Because in panel C, the 12 are really equally spaced. That's the difference. And so we're really looking to understand the formation of these super lattice patterns, as called by the experimentalists, or we'd call them super hexagons for the purpose of this talk. So great. So we kind of talked about a little bit how to convert our PDE into ODEs, but also to try and understand how we might look at nonlinear modal interactions. And before we go ahead, let's pull back and look at a simpler case. Here we see 2 different pictures. They look similar in certain ways. They both have 2 length scales, and at each length scale they have 6 wave vectors. And if you look at it a bit, it looks like the right panel, the inside circle has just been rotated to be aligned with the outer circle, right? The wave vectors are aligned. Now, one on the left is what we'd call a generic family, whereas the one on the right is what we'd call a special family. What is generic about these systems and what is special about the other? Well, we can look at the possible interactions by adding up wave vectors and combinations of them. So for example, in order to identify a second order interaction, we would add up 2 of the wave vectors and so on. And this is a kind of wave vector triads, kind of an idea that's been talked about in turbulence analysis and so on. So it's very similar. We're just adding up n wave vectors and trying to understand if their addition adds up to 0, then we know that that term must contribute in the evolution equation for each of those wave vectors. That's the idea we're going with. And in a generic family, we have the linear interaction. So we have the Z1 term in the Z1 dot equation. In combinations at the second order, we only have the hexagonal interactions, which we expect to have because we are in a hexagonal lattice. So for example, we can have K2 bar and K3 bar adding up to K1. And that's indicated by the Z2 bar and Z3 bar, which are the corresponding amplitudes of these wave vectors in the amplitude equation. That's term, because it arises from such a hexagonal interaction, we call it the hexagonal interaction term. And of course, when we move on to combinations of 3 wave vectors adding up to 0, we have many such combinations possible, and most of the ones that you see here in the generic, all of the ones that you see here in the generic family, think of them as taking the linear term, which is just Z1, and adding to it some combination of wave vectors that add up to 0. So if you take K1 and then add K1 and K1 bar to it, you still have K1 left at the end. And that is the first term Z1, that's the term Z1 times mod Z1 squared, and so on. So this is really all the terms we would expect there to be present because we have the wave vectors that we've chosen. So that is why it is a generic case. Whereas in the special case, because the alignment of the wave vectors are coincident, for example, along K1, the ratio of the inner circle to outer circle is 1:3 in this case. And it's a special value of this ratio because at this point, we can have, for the first time, 3 of the small wave vectors Q1 adding up to give us 1 of the vector K1. So correspondingly, in the amplitude equation for Z1, we would have a term W1 cubed. And that's what we see here. So if we want to analyze combinations of 6 wave vectors at each length scale, like the one shown here, we can consider the special case to be the one that we analyze. And if we set the coefficient of the W1 term to be 0, we would recover the results for the generic case. So that's the same idea we want to kind of take on for the 12 and 6 case, which is what we do here. The left is a generic case, and the right is this specific square root of 1/7 case. And this kind of gives us the rationale because we see that the generic term has the linear term, the hexagonal quadratic interaction, and then we have the expected cubic interactions. Whereas in the special case, in addition to all of this, for the first time, we also have an extra second order interaction. We have an interaction where K1 is given by the addition of K4 bar and Q1 bar. So we can, if I had a pen, I would show you the vector addition, but at least one of the extra interaction is kind of shown there. For example, we see that in the equation for Z1, we would have an extra term at the cubic order, which involves the addition of K4 bar. And then what is plotted there is Q2 bar and Q3 bar. They add up to, again, go back to K1, and that would be an extra cubic term in this amplitude equation. So we identify the case with the most number of extra terms, and that happens to be this Q equals 1/7 ratio. And so we try and understand this system so that we can try and recover other generic forms by setting certain coefficients to 0 in this case. So let's go back and think about how am I going to make a PDE model that has 2 length scales, but additionally, we want to ask of it certain conditions. Now, the thing that we can talk about when we're designing a linear operator is its associated linear dispersion relation in Fourier space, because that is nicer. It's just a function to think about, so we can impose certain conditions on it much easier. And then we can take the inverse Fourier transform to kind of get the linear operator. So that's what we do. So for our sigma of k, which is our linear dispersion relation, we want to enforce reality. By enforcing reality, what we mean really is that we want wave vector combinations and their conjugates to have the same value, so that our pattern at the end is a real valued pattern. And then we choose the length scales. So we want to be able to choose k equals q and k equals 1 and be able to vary this q as needed. We want the sharpness of the choice. By that, we mean the dispersion relation must vary very significantly around these 2 peaks so that we avoid having a whole range of patterns becoming, range of wavelengths becoming unstable or stable, because we're going to vary both the wavelengths, the stability of both the wavelengths. Now, we also want to enforce that large length scales are damped, and we want to have independent growth rates. So we want to be able to adjust the peak heights of these 2 independently. Now, this, if you translate it into conditions on the function sigma and its derivative with respect to k, is as shown in the middle of the slide. Now, all of these conditions then dictate that at least we need an 8th order polynomial in k, and inspired by the Swift-Homburg equation, which you see the inspiration is in the explicitly written final term, where we have the 1 minus k squared whole squared multiplied by q squared minus k squared whole squared. That is the part that kind of resembles a Swift-Homburg's system's dispersion relation. Additionally, we have this extra first term, which is introducing all the additional constraints that we've kind of set for this. If we were to kind of take away the last condition, that we want independent growth rates, then we revert back to the Lifshitz-Petrick model, which is simpler, but of course, as I said, it does not allow us to independently vary the two growth rates. Other than that, it's the same system. So this is how we design a linear operator, and motivated by the Faraday wave system, we look to add what nonlinear terms we expect this PDE model to have. And in this case, we choose 3 different nonlinearities. It might seem a bit, if you look at the second term, which is Q1 times U squared, it is the same polynomial second order nonlinearity, which allowed us to break the symmetry of U going to minus U in the Swift-Holmberg system. So we keep that. We also keep the next term, which is Q2 times U times the Laplacian of U, because that behaves similar to how U evolves. Laplacian of U behaves like U, so it still is variational. And we also introduce in the third term a non-variational term, which takes into account gradients in U, but in a different way. So it takes into account the gradient U squared, mod of that squared. And so we have, in some sense, 3 different second order nonlinearities, which could work together, or they could compete with each other. We're definitely going to talk about that. Now, we can perform the weakly nonlinear analysis, and at the end, if I assume full symmetry, by full symmetry, what I mean is we assume all of the wave vectors at the outer circle here have the same amplitude z instead of zj. All the zj's are equal, all the wls are equal. If we assume that, we end up with the equations that is shown here. So now we started with 3 different nonlinear terms, but we ended up with nonlinearities at the second order, which are reminiscent of just the z times z and the z times w. So here, the term that has z squared is coming from the hexagonal interaction, which we expect to happen because we have a hexagonal lattice. And similarly for the w squared term in the w1 equation. It should actually be w equation. Sorry about that, just noticed it. They are both the hexagonal terms. Now, the other 2 terms are really the more interesting ones because they kind of, in some sense, allow for crosstalk between the 2 length scales. This is clearly more apparent in the QZW term because we have a Z and a W adding up to a Z. Now, that gives us the kind of triads we talked about where 2 large wave vectors add up to a small wave vector. But of course, because the value of the wavelength ratio is less than a half, we don't have a corresponding ZW term in the W equation because 2 of the small wave vectors in this case will not add up to a large. But of course, we have the Z squared term. So we are really looking for, and the coefficients of these 4 terms in the amplitude equations are related to the original coefficients of the nonlinear terms as shown here. That's all right. And with that, we're looking for steady solutions to these equations. And if we look at steady solutions, we can just set the left-hand side to 0. And what we really have here are, if I didn't know what Z and W were, I just say, okay, I have some parameters and I have 2 cubic equations and they are coupled. So that is what I need to solve to get an answer for what values Z and W can have that satisfy these 2 equations simultaneously. Now, great, is that the only pattern we can have? In order to do this, we perform a cursory scan of the PDE's phase space by doing some simulations, and we recover some simple patterns like the flat state or the uniform state, where, as shown in the middle column of the table, all of the amplitudes are 0. We have 6 Z amplitudes and 3 W amplitudes. Because of reality condition, we don't have more. We only have 9 unknowns. And we also recover stripes, both at the Z scale, the Z amplitude and at the W amplitude. Of course, we also have hexagons of Zs. And additionally, now till these first 4, the number of unknowns that we need to solve for are either 0 or 1. And if we have only 1 cubic equation to solve, we have well-developed methods that we can do it by pen and paper and analyze the behaviors of this pattern, where it becomes unstable again, and so on and so forth, using equivariant bifurcation theory. But if we go to more complex patterns, which is of interest in this case, we have patterns which are rhombs 1, 4, which is not shown here, but at least look at the last two, which is the star and the super rectangle. Examples of those states are given in the panels below. The left-hand side is what we'd call a star, and the right-hand side is a super rectangle. And what you're seeing here is very contour levels in U, but if you look at the amplitudes of the patterns in Fourier space, we see that they have different symmetries, but the number of unknowns is not one. In the case of star, there is 3 clearly defined unknowns because the 6 Zs have been split into 2 groups of 3, and there is 1 unknown in W. Similarly, in super rectangles, we have 5 unknowns, and the symmetry there is much more reduced symmetry. So in these cases, direct solution is not possible, and we need other methods. We can think about, okay, if I have 2 coupled cubics, I could use the method of resolvence and convert them to 1 9th order polynomial. That's possible. And then try to solve for all of the roots of that 9th order polynomial. Or we can also use other global methods such as homotopy methods, and that is the line that I want to talk about, because the nice thing about using homotopy methods is that we can arrive at all of the solutions simultaneously without having to guess any of them. So that's a nice thing, and it's a globally convergent method. So and this is a slide explaining, I mean, I use a software to do this. I use the software Bertini to do this. And maybe some of you have known of this, but if you don't, this is just a 1-slide introduction for some numerical algebraic geometry. So as the picture shows, we have a start system G of Z, and we have a target system F of Z, and we need to define a homotopy, capital H, that kind of smoothly takes us between these 2 endpoints. And the choice of the start system is important, because what we need to do is identify the root count in our original system. And if we are considering the 2 coupled cubics, we need 9 solutions, and that is the upper bound for isolated solutions. And we then construct a start system which has the same number of solutions, isolated solutions. So the simplest case would be if I were to take 2 cubic equations, I could just take Z cubed minus 1 equals 0 and W cubed minus 1 equals 0. And all of the other coefficients that are here, for example, coefficient of Z squared, coefficient of ZW, consider them that we've set it to 0. And that system, Z cubed minus 1 equals 0 and W cubed minus 1 equals 0, still has 9 solutions. It's just that it's not even a coupled system in the sense that we have any cross terms. So slowly we start from that system and increase the coefficients of the terms towards our target system and keep track of what happens to the solutions. And we could have some of the solution parts, like the purple ones, blow up to infinity. We could have some of them become singular, that multiple parts converge. And neither of this is a scenario that we want to actually have. So we could pick a good homotopy, but in most softwares listed below, the software chooses the homotopy for you, and there is a gamma trick, which is if you choose a random complex number for the gamma in the homotopy, you are guaranteed that all of the singularity behavior, like blowing up and the singular path crossings, all happen very close to the target system. And if we can do that, then there are many endgame kind of strategies to handle this, and the software does this for you, and you get a list of all real finite solutions, which are the green parts that stay finite and stay isolated throughout this homotopy. And that's a nice thing to do. So what does this allow us to do? As I said, it gives us all of the solutions, and it also gives us, without having to guess for any of them, we could vary the parameter and repeat this procedure again and again to kind of get an idea of how many real solutions, real finite solutions exist at every parameter combination. And that are the results that we're seeing here. Sorry for the notation change. It's from another write-up of this. So mu is R1, nu is RQ. So these are the linear growth rates. And along with this, the other parameters in the system are the actual coefficients of the second order nonlinearities. And for the case we see here, the only non-zero one of them is the u squared term. So there's only q1 there that's non-zero. And in this case, then if we calculate the value of these cross products that we talked about, the qzw and qzz, they are, the product is greater than zero. Now, why is this interesting? What it says is if this product is greater than zero, then we have our nonlinearities actually reinforcing each other. So they're not competing with each other. And in this case, we see on the top left panel existence diagrams. So for a chosen combination of parameters mu and nu, the color indicates the number of real finite solutions that we find, all of which have the same symmetry. So there is not just one superhexagon, there is 2 or 4 or 6 superhexagons possible at the same parameters. And the second panel, in the panel on the right and the top row, really just shows us a zoomed in view of the codimension 2 point. And really we see how complex the kind of number of solutions, the existence diagram is. And this is still something that we're trying to understand how to do the bifurcation analysis for without just resorting to a numerical way of getting them like we've done now. So, but we can clearly see the locations of where the number of solutions changes from 2 to 4 and then 4 to 6. And this would happen at possible successive saddle node bifurcations. And these lines of change of color really are the loci of these saddle node bifurcations. That's what we're seeing. And the panel on the bottom gives us the stability regions for these patterns. And by substituting them into the Jacobian, we can find out how many of them are stable. In this case, it so happens that there's only one stable superhexagon, and the locations where they are available is shown in parameter combinations in the picture here. So that's one thing. If we were to look for stars, which have 5 unknowns, we're really solving 5 coupled cubic equations. So the number of possible solutions is 3 to the power 5 at every point. Out of that, how many of them are real and how many of them are finite? We have here the maximum number of possible finite states is 4, apparently, for the case that I've chosen here. The reason I've chosen a different case here is to kind of indicate another possibility, which is you have competitive nonlinear modal interactions, and that is indicated by the product value of qzw times qzz being less than 0. It seems to be more complicated in the sense of regions of existence, but if you look at regions of stability, we still recover just 1 star pattern possible. Now, the whole kind of trying to understand the formation of complex patterns when the ratio of length scales is less than 1/2 kind of talked to us to look at these different reinforcing or competitive second order interactions. And we kind of find that this product is a nice way to identify whether we have competing or reinforcing nonlinearities. And the kind of thing that we're trying to, how do I say with a bit more certainty is if we have mutually reinforcing nonlinearities, we would expect to see, for most parts, just temporally steady state, stable, steady equilibria. But if we want waves or time-varying solutions or even spatiotemporal chaos, they would be more prevalent in the cases where the nonlinear interactions actually competed with each other. And that's the kind of diagnosis we're trying to go towards, but this is where it is. So this is kind of like, I've run more than half the time, but this is the most kind of intensive part. The next is, let's look at a case where the wavelength ratio is greater than 1/2, as indicated by the Fourier spectra on the last panel on the first row. And this is actually a spectra, as it says on the title, that is obtained from experiments of soft matter. So now the motivation is kind of shifted from a fluid system of a Faraday wave to something like polymers and how they self-assemble when they crystallize. So if you think of, if you look at the first picture on the left, we have a tri-block copolymer. By that, what we mean is there's 3 different strands of polymers. They're attached at the central gray dot. Now, if we take a bunch of these and put them into a jar or a domain and reduce the temperature, they start to crystallize. And on the third direction, on the Z direction, they don't do anything interesting. They just uniformly align themselves in the 3 directions. Whereas if you look at them from the top, that is the panel that is the view that you're seeing in the third panel. Thank you, in gray. And the gray image comes from a scanning electron microscope, and superimposed on it in red is just the tiling or the decoration that describes this. And we see here that the tiling is very interesting because it has only kind of these rhombs and equilateral triangles. And if we have these kind of squares and equilateral triangles being sufficient to tile a panel, we immediately know that it does not fall into one of these allowed crystallographic symmetries, or it basically says that this arrangement is not periodic. And true enough, if we take the gray image and take its Fourier transform, we end up with the picture that you see finally in Fourier spectra. And what we see here is very similar to what we saw in the Faraday waves. We have 2 circles, well defined, and there are 12 peaks. So it looks a bit like a clock face at each length scale, and the clock faces of each of the wavelengths are slightly rotated with respect to each other. So this is very similar to the picture of the quasi patterns that we got from Faraday waves. Of course, here the physics is completely different, the length scales are completely different, and we still get back the same complex spatial pattern. It's spatially complex, but temporally it's just steady. Now, similarly, other non-allowed or forbidden crystallographic symmetries were observed in 3 dimensions as well. And there in 3 dimensions, one of the not allowed symmetries is that of icosahedral symmetry. But there have been multiple realizations of such icosahedral symmetry in 3 dimensions at the atomic scale. So there we go. At Faraday waves, we saw patterns at millimeter scales. At soft matter, we see them at nanometer scales, and metallic alloys at the angstrom scales. And so there is something that needs to, or something that can be done to analyze these patterns and how they form independent of the physics behind it. So what is the minimal requirements to generate both 2D quasicrystals or 2D quasi-patterns? And by that, what we mean is things like the picture above, and 3D, so in bulk. Can we create them from a simple PDE model of a soft matter? That's what we're trying to do. And the equation above looks a bit more familiar now. We've looked at the version of it without the Laplacian in front, and there's reason. If we were to think about an associated free energy, which is written in the MatCal F, that the functional derivative of that with respect to the scalar field then gives us a dynamic. And that is how we can even write the Swift-Homburg equation. Additionally, here we have the Laplacian to indicate that this system actually has something conserved. It evolves in a more restricted manner because, for example, in this system, you can think of it as being the number of particles in the system. So the total mass is conserved because the physical system is just undergoing crystallization. So you can't lose anything or you can't add anything. You can just transform from one to another. So, but the actual physical quantity that's being conserved is called the chemical potential. And for us, mathematically, if you want to look at it, it just introduces this extra Laplacian in front. So what we once had an 8th-order polynomial in K, we would now have a 10th-order polynomial in K, but actually I should say it's a 5th-order polynomial in K squared. And we have the linear operator. Again, it's going to be the same linear operator we had before, which had all these properties that we liked, such as, enforcing reality, sharpness of selection, and so on, an independent variation of the 2 length scales. And we have the same nonlinear terms as the Swift-Homburg equation. Keep it simple, just polynomial nonlinearities in this case. And we kind of want to connect this linear operator, or the dispersion relation in this case, thank you, with how these soft matter materials interact with each other. So in this case, we want to connect this dispersion relation to how two micelles interact with each other. If we have two micelles, as shown in this picture, and they are far enough away, they don't feel each other, and if they come closer, they would have certain level of resistance when the coronas merge, and they would have even higher levels of resistance when the cores start to merge. However, because this is soft matter, this interaction potential never becomes infinite, and so we have, in a sense, for the function v of r, a smooth, finite function for all values of r. Because we have that, we can take the Fourier transform of it, and that's how we recover this two length scale selection dispersion relation as shown in the right figure. Now, of course, the Laplacian in the dynamics is the reason why we have a neutral dispersion value, neutral value of sigma equal to 0 at k close to 0. If we didn't have that, we would have a possibly a negative value in the previous system that we saw before. So again, we have the same parameters here. We have the two growth rates, and we have, in this case, a capital Q, which is the strength of the nonlinear interactions. Of course, we can choose also the length scale ratio, so that gives us one more parameter, little q. So we take a nominal value of capital Q in 2 dimensions and choose that our sharpness of the peaks is relatively sharp. We can do that by controlling what sigma naught is. Negative values imply that the minima in the sigma of k curve are more negative, and that would control how sharp the peaks are around k equals 1 and k equals q. So we choose a negative value that's sufficient, and we imprint a dodecagonal symmetry, or we require we kind of pre-select the wave vectors and say these are the wave vectors that are non-zero amplitude, and we do that by choosing the wavelength ratio to be 1 over 2 cosine pi over 12. Why is this weird number chosen? The weird number is the angle between two wave vectors that add up to another one at the length scale that we want in this case. So that we have 12 of them adding up to 12 on the other length scale. So it's vector addition that gives us this number, and the remaining two parameters are varied in a circle, and we recover regular patterns such as stripes, not shown here, hexagons of both up and down varieties, and additionally the 12-fold quasicrystal shown here in the middle panel for the up variety, and the down variety on the third panel. So nice, we basically put in the requirements that we will have two length scales and some level of nonlinear interactions between them, and that seems to be enough to get two-dimensional quasicrystals. Does this work in 3D? And in 3D, we choose the icosahedral symmetry and a nominal value of the nonlinear interaction, so Q is 1, but in 3 dimensions, the sharpness of the peaks has to be much, much smaller. So it has to be really sharp because we have a whole load of other patterns that are possible and patterns that have symmetry reduced patterns that are possible. So we increase the value, or we decrease the value of sigma naught to minus 100, and we find that we can form icosahedral quasicrystals in this case. So yes, the answer seems to be that we need just 2 length scales, and they need to be rationally related and some level of nonlinear interactions, and we can form quasicrystals in 2 and 3 dimensions. So can we do this similar kind of weakly nonlinear analysis and get coupled equations for them and try to use homotopy methods to look at existence? That's the kind of connection between both of these halves of the talk. I will finish in like 2 minutes or something. Am I okay with that, or do I have more time, Lachlan?
2 minutes is probably good. I'll copy a few minutes.
Yeah. Okay, cool.
That's okay.
So it's kind of interesting, but kind of the story that we've seen before in some sense on the other side of Q less than a half is we have multiple solutions, and they kind of this analysis is able to identify the locations where saddle nodes increase the number of possible solutions and they emerge in pairs. And we can take a kind of cross section in this along the theta direction and see how many of them are stable. So on the left, what you're seeing is existence. There are 8 solutions possible around this line R1 equals RQ, whereas if you look at stability, we really find that there's more than one of the solutions stable dynamically at the same parameters. So if we look at some of them, we can look at even solution branches in different families, but if you look at them, this is the 2 solutions that our ordinary differential equation or our reduction says exist and are stable in the ODE system. So they look, if you look at them, like one is the negative of another, like wherever the panel A has yellow, panel B seems to have blue. They are almost the negatives of each other, but not quite. They have some points of differences. And the question really is to ask, okay, I do all this analysis on the ODE system. How many of these states actually persist into the PDE? Do they remain stable? Do they even exist in the PDE? And in this case, it seems to be that if I give them as initial conditions to numerical iterative methods, I converge to both of these states. And the first one looks very similar to the guess, and the second one actually looks very different to the, it looks more jagged to the guess, but you find that such metastable states exist. In this case, they're not the globally stable states, but that doesn't matter. In this case, what we're saying is we can identify conditions where novel patterns or multiple states become possible. So this whole idea, in summary, is you know, the third point really is what I'm trying to say now, that homotopy methods can be used to obtain reduced symmetry solutions and identify interesting parameters where we can probably go back and probe with more detailed models. Like in soft matter, you can do molecular dynamic simulations. In Faraday wave equations, we can actually simulate the proper equations instead of this simple PDE and so on. And with that, I mean, this is a summary of my talk, and thank you for your attention. I'm happy to take any questions.